Let's take a look. So let's take a look at the following example that deals with calculating the magnetic field inside an NMR spectrometer. So suppose that we have the carbon-13 isotope. The carbon-13 isotope has a magnetic dipole moment of 0.7023 multiplied by the Bohr magneton μb, where μb is simply a constant. So we take our carbon-13 atom and we place it inside our NMR spectrometer, and the NMR spectrometer determines that the frequency change, also known as the chemical shift of that atom, is about 42.6 megahertz. So what is the strength of the magnetic field inside that NMR spectrometer? So before we make the calculation, let's actually describe what is taking place inside the NMR spectrometer. So we have the nucleus of our carbon-13 atom as shown. Now, when no magnetic field exists, when the NMR machine is basically turned off, the nucleus of the carbon-13 has a certain magnetic dipole moment that is shown in this diagram. So the charge in that nucleus basically spins on an axis, creating our magnetic dipole moment that points along this axis. Now, as soon as we turn on the magnetic field inside our NMR spectrometer, let's say the magnetic field points this way, what happens is this magnetic dipole moment begins to precess about this precession axis. So this precession axis shown here is parallel to the magnetic field lines as shown. So basically, this nucleus of the carbon-13 isotope begins to precess as shown in this diagram. Now, the next step in the NMR machine is basically to send an electromagnetic wave directly at our atom. So this electromagnetic wave is commonly known as the radio frequency pulse. And if the radio frequency pulse contains just the right frequency, it contains just the right amount of energy, what happens is, as it hits the following nucleus of our carbon-13 isotope, it flattens out our precession as shown in this diagram, and also it allows the nucleus of the atom to transition from the lower in energy spin up state to the higher in energy spin down state. So basically, if we imagine that this is the spin up state, it basically flips and basically precesses about the different axes that points in that direction. So that is not shown in this diagram, but you can imagine that it flips so that it goes from the spin up state to the spin down state. Now, what happens in the final step of the NMR machine? So basically, we turn off all our magnetic fields. So we turn off this static magnetic field that we are trying to find, and we turn off the coils that produce the RF pulse. So once we turn that off, what happens is our protons inside the nucleus and our nucleus of the atom as a whole basically flips back to its initial position as shown in diagram 1. So this is shown by diagram 4. Now in the process, because it goes from a high in energy quantum state to a low in energy quantum state, it releases a photon of electromagnetic radiation that has a frequency that is given by 42.6 megahertz. So now we want to use this information to calculate the magnetic field B. So how exactly can we calculate the magnetic field B? Well, notice that the frequency of this electromagnetic radiation, the photon, determines the energy. And the change in energy of this photon is given by h times f, where h is Planck's constant and f is this frequency given in hertz. Now, in our discussion on NMR, or nuclear magnetic resonance, we said that when our nucleus jumps from the lower in energy spin up state to the higher in energy spin down state, there is a gain in energy that is given by 2 multiplied by the magnetic dipole moment multiplied by the magnetic field. So we can equate this to this and now solve for our magnetic field B. So basically, the amount of energy carried by this photon is given by this. So now we can solve for B, we get the following result. So we know that mu C is equal to mu C equals to 0.7023 multiplied by the Bohr magneton. Now recall that the Bohr magneton is simply a constant, and the Bohr magneton is equal to, we have E, which is the charge on our proton, multiplied by Planck's constant H, divided by 4 pi multiplied by the mass on a single proton. So we can take our mu B, the Bohr magneton, and replace it with this ratio as shown. And now we can take this and bring it to our numerator, and we get the following result. So notice the H's will cancel, this 2 will cancel, this 4 becomes a 2, we have this result. And now we can plug in our known values. We know the mass of the proton is about 1.6726 times 10 to negative 27 kilograms. The frequency in hertz is this, multiplied by 10 to the 6, that gives us hertz, and the mass of, or the charge on the proton is positive 1.6 times 10 to negative 19 coulombs. We plug in our values, we multiply and divide, and we get that our static magnetic field inside that NMR spectrometer is about 3.98 Teslas or 4 Teslas. So basically what happens is our magnetic field is very, very strong, and this magnetic field, this high magnetic field, allows the frequency to be relatively low, and that means this low frequency will not be able to damage these photons that are emitted. Because they have a very low frequency, they will not be able to damage our cells found in the body. So we see that the MRI technique, or the NMR technique, the MRI uses the NMR technique, basically produces electromagnetic radiation that has a relatively low frequency, and so it does not damage the tissues and cells found inside the body.